Good morning, everyone. This is Dr. Quinton. I'd like to welcome you back to my chemistry class. We're going to continue the lesson that we started last week on thermodynamics. But before we get into any new material, I would like to review some of the material that we've already gone over. Now, as we mentioned last week, thermodynamics studies how heat changes as it moves from one thing to another. We defined heat as basically the random motion of particles. For example, here we see the kinetic energy of gas molecules in this container. Now we know that heat is basically kinetic energy, which means moving energy. So the movement of the gas molecules reflects the amount of heat in the gas. The more heat these molecules have, the faster the molecules move. Also, keep in mind that heat always flows from hot to cold. Energy will always flow from a region where it's high to a region where it's low. When something has a lot of energy, it's considered high energy, it'll feel hot. If something has a small amount of energy, it'll be low energy and it'll be cold. Now, ultimately, we will be talking about how energy transfers in and out within chemical reactions. Now, we've talked a little about this before last week. So chemical reactions always involve energy transferring or moving between different compounds, between the compounds that represent the reactant, the starting material, and the products, the ending material. So this energy is either going to be absorbed or it's going to be released. And the making and breaking of bonds, so the making of bonds in the product and the breaking of bonds in the reactant, involves energy changes between these two. Now, we've already studied these energy changes in relation to how bonds are being made or broken. So the first type of reaction we considered was endothermic reactions. Endo means into. So these reactions take in or absorb energy from the outside. Now because they're absorbing energy, they feel cold to the touch. If you touch something that feels cold, that means you have more energy than the object that you're touching. So energy is flowing from hot to cold, so it's going from the outside, from the surroundings, into the object. Now, in chemical reactions, this usually reflects the fact that more bonds are being made in the product than more bonds being broken in the reactants than are being made in the products. Because absorbing energy is an endothermic process. Making bonds, or breaking bonds, is an endothermic process. Conversely, we have exothermic reactions. Now, these reactions give off heat energy to the outside. They feel hot to the touch, because energy always flows from hot to cold. So if something feels hot, that means the energy is flowing from that object to you. And this, in terms of chemical reactions, this reflects the fact that more bonds are being made in the products than are being broken in the reactants. In terms of looking where the energy is actually going, for an endothermic reaction, for a reaction that's absorbing energy, this means that the reactants have less energy than the products. If the reaction is absorbing energy, if energy is going into the system, then it means that energy has to go somewhere. And in the case of a chemical reaction, all the energy that's being absorbed during the reaction is being stored in the product. That's why we show that the product has more energy than reactants. In an exothermic reaction, heat is given off. That means it feels hot to the touch. So where is the energy coming from that makes it feel hot? Well, all the energy that's being stored in the reactant, as they react, they give off energy, so that afterwards, when we have the products left, the products have less energy than the reactants. If something is feeling hot, the energy has to come from somewhere. In this case, the energy is coming out of the reactants. Now, for the purposes of our discussion, we're going to consider heat to mean one of two things. It will either equal the amount of thermal energy contained in something, so if something is hot, it has energy in it, or energy that's transferred into or out of something. So the amount of thermal energy contained in something, this would be analogous to something that's a solid object. It's not moving, but all matter has mass, and all matter contains molecules, and those molecules have some sort of movement. That means they have some sort of heat in it. It may not seem like it's hot, but there is movement within those molecules. Now that means something either can become hotter or colder. So that means we'll also talk about thermal energy being transferred into something or out of something. I also want to re-emphasize the difference between heat and temperature. We know that if something is hot or cold, then we know that it contains either a lot of energy to make it hot or a very small amount of energy to make it cold. That's referring to heat. Now for temperature, that is simply telling us how much energy is in something. So if it's hot or cold, we know that it has either a lot or a little energy. If we say how much energy it has, then we're talking about temperature. Now whenever we're measuring something, that usually involves numbers. But you can't have numbers without a unit, because a number without a unit is useless. It doesn't tell us anything. So since heat is a form of energy, we know that there are certain units that go along with with energy. And we're going to use either joules or calories as a unit of energy. So now what are each of these? We really haven't talked about joules too much, so I'm going to introduce that now a little bit. Joule is the international unit, that means the metric system unit for energy. It basically means it's the amount of force in newtons that is needed to move something by 1 meter. So if you apply a force and you move it, that means energy is involved. Now we're going to talk about this just a little bit in just a little while. Now in terms of calories, now we talked about this last week. A calorie is the amount of heat required to change the temperature of 1 gram of water by 1 degree Celsius. That is the formal definition of a calorie. Now the calorie you're used to thinking of in terms of food is would be 1 kilocalorie. Notice the big C, this means kilocalorie, that means 1,000 calories. So 1 big calorie, 1 kilocalorie is equal to 1,000 calories. And to convert between one to the other, 1 calorie is basically equal to about close to 4.2 joules. And we've also talked about specific heat. Now specific heat is the amount of energy that something can absorb before it begins to show a change in its temperature. So the greater amount of something that you have, the more mass you have of something, the more energy it can absorb before its temperature changes. Now remember, temperature is a measure of how much kinetic energy something has. That means how fast the molecules are moving. Now there's a certain force that keeps those molecules together. But if you add enough energy to something, those molecules can be excited further and they'll start moving further apart. It's sort of like changing from a solid to a liquid. So the specific heat gives us an idea of how much energy it can absorb before it starts changing from a solid to a liquid. Now different materials can absorb different amounts of heat before the molecules start to move a lot, and then they start changing temperature. And that's what we refer to as our delta T, is our change in temperature. It's the difference between the temperature that was before absorbing heat and the temperature that it has after absorbing heat. So basically this equation tells us that the amount of heat that something can absorb depends on how much you have of it and its ability to absorb heat, which is going to be reflected as a change in its temperature. Now, on the first day we met, when chemistry class first started, I told you that scientists basically do one thing. They make observations, and then they come up with ideas based on what it is they're seeing. Well, in thermodynamics, we deal with these quantities or properties that we can measure, and they help us to describe what we're looking at. But then we raise the question, how do you know what you're looking at? Well, in thermodynamics, that's a fairly important distinction because we have to decide what it is we're focusing on and how that relates to everything else around it. So in thermodynamics, we have to decide what the boundary is between what it is we're looking at and everything else. Now, at this time, the teacher is going to pause this presentation, and she has a small video to show you. It's about 30 seconds that tries to illustrate a little bit about what this system and surrounding is. So teacher, if you would please pause this presentation and then bring up the video, please. Now I want to talk a little bit about how this distinction between the system and the surroundings applies to us in chemistry. Now, as I said in the previous slide, we make a basic assumption about how we can divide something into a system and surroundings. Now, this boundary between the system and the surroundings can be as real as the walls of a beaker that separates a chemical reaction from the rest of the universe. And in fact, for our purposes, that's all we really need to consider mostly, is the system is going to be the reaction that's happening inside some sort of glassware. The surroundings is going to be everything else. That means the rest of the universe. So in this terms, we're going to be talking about our reaction is our system, and then the surroundings is everything else. Now, in thermodynamics, it's important to make the distinction as to which way the energy is going to make the change. So how can we figure out which way the energy is changing? So basically, our delta E means change in energy. Well, as an example, think about water in a beaker on a hot plate. So you filled a beaker with water, you put it on the hot plate, you turn it on, the hot plate starts to get hot. Now, when the hot plate's on, the water is going to begin to get heat. The heat is going to move from the hot plate into the water by conduction. And as the water gains heat, the internal energy of our system, of our water inside the beaker, starts to increase. Now you'll notice here I have a small equation here. All right, E sub F minus E sub I equals a positive change in energy. All right, now let's define these terms. All right, E sub F is down here. That means the final amount of energy. That means the amount of energy that's in our system, in our water, once it absorbs energy. Now E sub I, that means initial or beginning amount. So this would be the amount of energy in our water before putting it on the hot plate. Now, if the hot plate is on and the water is on the hot plate, then that means that after a while, the water is going to have more energy, it's going to have more heat afterwards than it did in the beginning. Now, we always show change in energy by looking at the amount of energy afterwards minus the amount of energy before. In this case, if our system is absorbing energy, that means the amount of energy that we end with is going to be different from the amount of energy we begin with. If that's the case, that means we have more energy ending than we do beginning. So we take our ending energy minus the beginning energy, and we're going to end up with a positive number. So big number minus small number means it's going to be a number that's greater than 0. That means it's going to be positive. Now, if we take the beaker off the hot plate, now the water begins to lose heat. And as it does, the heat is going to be moving from the system into the surroundings, and the amount of energy inside our system, inside our water, is going to decrease. It's going to start going down. If that's the case, then it means that after a while, the amount of energy in the water is going to be less than the amount of energy we started with. So now the water is giving off heat, so now we have a certain amount of energy inside the water. After a while, that energy is going to be lost to the outside. Energy from the hot water will basically move through the boundary and then get into the surroundings. So the amount of energy inside is going to go down. If that's the case, that means now we have a small amount of energy afterwards. We subtract the amount of energy that we started with, and we're going to end up with a negative number. Small minus big equals a number that's less than 0. So what I want you to get from this is that if energy is going into a system, that means the energy change is positive. If energy is going out of a system, that means our energy change is negative. Okay, now we come to our seed question. So in reference to what we just described for our system and surroundings, how do you think the changes in energy, the delta E, either positive or negative, how would this correlate with changes in temperature? All right, at this time, the teacher is going to pause the video, give you about 30 seconds to a minute to discuss this. The teacher will call on some of you to get an idea of how you understand this, and then we'll continue the video. Pause the presentation now, please. Okay, we're back. Now I'm hoping that this situation seems familiar to you. Remember, we have energy going in, and we have energy coming out. Now this is something that we've seen before. So if the system is showing a negative change in energy, how would this feel, and how would a positive change in energy feel? Well, a negative energy change is going to feel hot because the system is giving off heat. If that's the case, that means it's going to feel hot because the object has more heat than you do, so it's going to feel hot. A positive change, since it's absorbing energy, that's going to feel cold. So this relates closely with endothermic and exothermic changes. Okay, now we're getting to the heart of today's lesson. So, two terms that we're already familiar with, and then a third term we're adding here. So, heat energy, and work. Now, all three are related, but they're not all necessarily the same thing. So keep in mind that we know that heat is a form of kinetic or moving energy. We also know that energy is defined as the ability to do work. That's been the definition of energy over a long time. We also know that if something has heat, that means that its molecules are moving. So the more heat something has, the faster the molecules are moving. Now, energy is defined as the ability to do work, but now that raises the question, what is work? Well, that's what we're going to get a better grasp of here in just a moment. Okay, now at this time, the teacher has another video to show you. It's going to be about a minute and a half. It just illustrates the idea of how we go about work. Okay, a note to the teacher that we're going to start this video about 2 minutes in and let it play until the end. So now, teacher, please pause this presentation and we'll be back in a moment. Okay, I'm back. Now, I know that video may have seemed a little basic, but we're going to break this down to help this make sense, to what we can actually get from it. Okay, now here's the relevant scene from that video. Now you'll notice that the boy is about to push on the chair. Now, where the chair is located now, this is our starting position, our starting distance. So it's a certain distance away from him. It's a position. Now, as the boy applies force, he moves the chair a certain distance. So now he's added that force to move it forward, and now the chair is at a new distance, a new position. Now, the amount of force needed to move the chair depends on how much the chair weighs and how much friction there is between the chair and what he's pushing it on. But basically, he will have to apply a certain amount of force in order to move this chair a distance. So this boy has basically done work on the chair. Now, work is done during energy transfer. So here's how we look at it. So work is equal to the force times the change in the distance. So we would calculate this if we knew the amount of force, which would be equal to the amount of the weight of the chair and the friction, and multiply that by the change in the distance between the beginning position and the ending position. That will give us an idea of how much work is being done. And this we could measure as joules or calories. So work is a form of energy. It's the ability to do work, so we can use the units of joules and calories in order to measure work. Now, some of you may be thinking, well, Dr. Quinton, that's all well and good, but what does this have to do with chemistry? Well, we can also see work being done during a chemical reaction. So, what kind of work can be done in a chemical reaction? Well, there are two types of work that we see happening all the time. The first one is electrical work. Now, this happens by moving a current of electrons through an external medium. In this case, it would be like a wire. So as we move electrons from one place to another, we're doing work because the electrons, we're applying a force, the voltage, and the electrons are moving, so we're doing work. There's also expansive work, when something is expanding. For example, by changing its volume. So if we had a gas and we heated it up, and then the balloon or whatever was expanded, that means we're moving the walls of the balloon, so therefore we're doing work. If we're applying a force and something moves as a result, that means work is being done. But how is this happening? Well, remember, we know that heat will either be given off or... Sorry guys, I got a little flustered there. So we know that heat will either be given off or it's going to be absorbed. We also know that molecules will either slow down or move faster as a result. So as they give off energy, they're going to start slowing down because they're losing their energy to the surroundings, or they're going to move faster as they absorb energy. Now, when the speed of the molecules changes, it can also change how much work is being done. And folks, that brings us to the first law of thermodynamics. Basically, the law of conservation of energy. Now, this is very similar to the law of conservation of mass. So our formal definition is the change in the internal energy of a system. That means whether it's absorbing or giving off energy is going to be equal to the sum of heat that's gained or lost by the system. That means either absorbed or given off, and the work that's done by or on the system. That means the system is either going to act on something to do work, or the surroundings are going to do some work on the system. So what does this mean? Well, it means that when heat is absorbed or released by something, it can change the amount of energy in that something, either make it hotter or colder, hotter by absorbing or colder by releasing, and or the heat can go into doing work. Guys, if you remember, we defined the law of conservation of mass as meaning that however much material you start with, you've got to end up with the same amount of material. And we usually discuss this in terms of a chemical reaction. The amount of reactants that you have has got to end up in the same amount in the amount of products you have. Well, energy is the same way. However much energy you start with, you've got to be able to account for all the energy in the end. Now, if you notice our equation at the bottom of the screen, so the change in energy is equal to the amount of energy that's either being absorbed or released, and the amount of work to be done. Now, to help me illustrate this principle, we're going to look at how a car engine works. Okay, here's the cartoon of 4 pistons in a 4-cylinder engine. Okay, the area where the pistons are housed, this would be the engine block. So each piston has a shaft that's connected to a crankshaft. As these pistons move up and down, it turns the crankshaft this way, and then this energy is then transferred to the wheels to make the car run. So what we're basically doing is we're converting chemical energy in the gasoline to mechanical or kinetic energy to make the car move. Now, the way this works is usually there are 4 stages that happens to make this piston move. The first one is called induction. Now, the first phase is induction. What happens during induction is that gasoline vapor is taken into the cylinder, so it's drawing it in, and then in a moment it's going to be compressed. Now, as it compresses, then we're tightening it up, and then comes the power phase where the gas is ignited. And once that happens, the gas expands and pushes the piston down. Now, as that happens, now we're drawing it out, and it's beginning to cool off, and now it's pushing upward, and now it's pushing out all the gas, all the carbon dioxide and water that's created during combustion. And then we start the induction phase again, so drawing in some more gasoline. As we're drawing more gasoline. Okay, now move this video back a bit in order to make a point. Now, the point I'm trying to make is this. As we ignite the gas, as the gas expands, it changes its volume, and what that's going to do is it's going to push the piston downward as the gas expands. Now, as the piston is moving, we're basically doing. Remember, whenever we add force in order to make something move a distance, we're doing work on it. So we're transferring the energy from the gasoline into kinetic energy to make the car work. So we're using the force of the chemical reaction to make the piston move in order to change it to kinetic energy. Now, how does this apply to the first law of thermodynamics? Well, as a lot of you know, automobile engines are not the most efficient. They give off a lot of heat. But the point I'm trying to make is, all right, let's consider we have a hot source. In terms of our piston, this would be the gasoline being ignited inside the cylinder. So now we have all that heat coming out of the gasoline being combusted. Now, in this case, the heat is going into the gas, and the work coming out that we're going to see will be the piston that's moving. But not all the energy going into it is going to go into work. Most of the heat is going to be going into basically the surroundings. So our object here, our engine, is going to be our system, and then the surroundings is going to be either the rest of the engine or the rest of the car surrounding it. The point I'm trying to make with this is that however much energy you put into it, we should be able to account for all the energy that's coming out of it. So that means that the change in energy is going to be equal to the energy that's given off plus any work that's done from it. So whatever energy goes in must come out. Now, our energy that we're putting into it is going to be equal to whatever work can be done plus any energy that's given off as heat. Perhaps the next slide will put this into a little more perspective. So here we have an automobile. Now let's say that we put gas into it. Now, the gas represents 100% of the starting amount of energy. Now, once the engine starts burning the gasoline, up to 62% of that energy from the gasoline is going to be lost as heat, either friction or other different efficiencies. So some of it is going to be given to idling, the drivetrain, the friction that's going on within the engine, and then actually running accessories like the engine's going to use some of the energy to run some of the other functions of the car. And then only 14% of the energy from the gasoline is actually going into moving the car, which is the actual work. So what we're trying to mean by this, if we go back to the previous slide, we said that the amount of energy we start with is either going to be used to make useful work or is going to be lost as heat. So the point we're making here is that Q hot, that's going to be the energy in the gas, is either going to go into being lost as heat, or it's going to be going into doing useful work. So these two added together should equal this. That's why we say it's the law of conservation of energy. However much energy you put into it, you should get the same amount of energy coming out of it. Okay, folks, that's the end of our note presentation today. The teacher is going to pause this presentation in a moment and then hand out today's assignment. Once she's handed it out, then she'll come back and resume the presentation. All right, teacher, if you would go ahead and pause this presentation and hand out the assignment, please. All right, let's take a look at what I'm asking you to do today. All right, so here's number 1 for the assignment you just been handed out. So I'm asking you for number 1 to calculate the change in energy for each of the following cases. Now I'm only showing part A. There's a B and C with number 1, and also there's A, B, and C with number 2. So we'll just go over A part of number 1. Okay, so we're given the amount of heat being, in this case, being absorbed. Since Q is positive, that means energy is being absorbed. So it's be 51 kilojoules. And the amount of work is equal to negative 15 kilojoules. Now you may be wondering why this is negative. Well, it deals with whether or not the system is doing work on the surroundings or whether the surroundings is doing work on the system. So if the system is pushing outward, changing the distance, then it means that it would be positive. In this case, since it's moving inward, since it's negative, that means that work is being done on the system, so it's being moved toward it. All right, so how do we calculate the delta E? Well, guys, remember our equation. The change in energy is equal to the amount of heat lost or gained plus any useful work that's done. So if we look at our equation, we simply replace each of these values, these variables, with the correct number. So the amount of heat, in this case, that would be absorbed, is 51 kilojoules. We're adding to that the amount of work that's being done, negative 15 kilojoules. And our answer is 36 kilojoules. So this is the amount of energy that is that's being lost as heat, basically, or that's being absorbed by the system. Because not all the energy is going into changing the temperature. Some of the energy is also going to doing some useful work. All right, now that we've taken a look at number 1, would you go ahead and work on the others? Now keep in mind for the other problems, they're not straightforward calculations. They will require you to think a little bit about the concepts. Go back and look through your notes and see if you can understand what the question is asking you. And of course, the teacher will also be available to help you. All right, guys, thanks for your attention, and we'll talk again soon.